Okay, welcome students. This is the first day of Supernova week. We're going to be talking about supernovas, which are so far as we know, some of the biggest explosions in the universe. But we're watching. We're watching for everything that we can see. All right, but before we do that, I have a couple comments about exam 3. Here's a printout, just kind of a mock-up of a printout. And Jenny is again going to send these around for you. And I have done the blurb sheets for exam 1. So if you look at the on the home page below the picture of the observatory, there's a few links and stuff like YouTube and the homework list and stuff. There's now a link down there for the blurb sheets. And the blurb sheets for exam 1 are up. Now, I've got to do exam 2 and exam 3. I'll try to do them this week or maybe next week. It's kind of a painstaking process. But with the printout like this and the blurb sheet, you can get kind of a mini study guide to get ready for the final. Because what's with the crutches back there? Yo, are you walking around on crutches? You hurt your foot? Okay. Do you need to talk to me about anything? Okay. Check in with you after class. Yeah, good. Anyways, the final exam is going to be cumulative. So you want to study everything from exam 1. And everything from the first day in January all the way up until the end of next week. So homework X3, it's not a regular homework, but I want you to just answer one cinchy question. Do you want the printout or not? And Jenny will look for everybody that's got that one answered in the affirmative, and then she'll send it to you. So then you've done that for the first 2 exams? Okay. So she'll be doing that for you again for exam 3. Now there won't be any blurb sheet for the final because you won't see me again after the final. That's our last interaction. Okay, but for exams 1, 2, and 3, yes. Also, I completed grading the Scantrons, and I found 3 bloopers, and I got those squared away in the grade book. I also graded the clicking, and some of that is all the clicking is up for everybody, and so you can look at your full score, your exam 3 total. Now, as I mentioned last week, after exam 3, you can then start thinking of your best 2 out of 3. All right, because remember the grading procedure is best 2 out of 3 midterms, a final, 25 points for homework, 25 points for participation, 15 points for homework. So we've got all the homework going, we've got all the participation going. We don't have the final yet, but we do have 3 exams, so we can now do that maneuver. And you can do it mentally. I'll put a new row in your grades page maybe this week. This time of the semester, I am really overwhelmed with work, so it's just going to be crazy time from now until the end of April. But we're gonna get through it. Question?
Are you still waiting for the 2 most recent observatory sessions?
Oh, you mean this?
Yeah.
Way ahead of you. The answer is no. I've got them. I've got 2 big, huge piles. They're sitting on my desk. I've been getting a midterm ready for my other class this afternoon at noon today, so I haven't had time to alphabetize those, and because I got to alphabetize them, hopefully they're legible, and then I got to put them in the grade book and stuff. So, but I'll get to it. Don't worry. But I've got them. Last week I couldn't say that I had them, but now I have. I can say I've got them. So I know some of you have messaged me about it in web courses. Yeah, we got them, but they'll get up there in your grade book and stuff. Also, let me remind you again that if you are a person that cannot ever go to the observatory, or you just luck out that your schedule works out, so that you're shut out every time, we're going to have two extra credit assignments, bonus point assignments next week. One of them in class on Thursday, the last day of class, and it'll be like a little mini review that you'll do with your clickers, so bring your clickers. And then we'll do another mini review in web courses, kind of like a homework, but it'll be a little bit bigger, and that will be converted into some bonus points. And the in-class review, 4 and 4. So each of those, so even if you did not get a chance to go to the observatory, you'll still be able to get 8 bonus points, just like everybody that did go to the observatory at least once. All right, now questions about any of that? Yes, Daniel?
So with the exam spectrum blurbs, if we made an outline of each concept per blurb, would you say that's a good study, like a good main core study guide?
Ding, 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 ding. Not a bad idea. It is a mini study guide, really. And the way, except for the matching, the matching's not that, actually the matching is in the blurb sheet. But your question, do the blurbs taken together, can you form them into like a study guide for the entire semester? The answer is yeah. I never thought about it that way, except for the stuff that we're doing this week and next week. So Supernova, because they're not going to be in exam 3. But yeah, I mean, because I always say that any exam that I give is a reflection of, or is an examination or a test to see if you savvy the things that I consider important. Okay? And I always tell you, look at the lecture notes first. Let your lecture notes be your study guide. And that's because on any given day, I have to make an enormous amount of decisions what to cover and what not to cover. I mean, because we could spend an entire semester talking about comets only and have a lot of fun doing it. But so we got to, things to do, cover, we got to go through a lot of things. So every day I'm preparing lecture, I'm making decisions about what I think is important, and then the stuff I think, I'd like to talk about it, but it's not important enough. That goes by the wayside. So so as I said, everything in lecture is the stuff that I consider important enough to include. And therefore, since my exams are oriented to the lectures, the blurb sheets are going to express that as well. Slightly different way, but yeah. So as I said, they make a nice little mini study guide on their own, and taken together a nice little mini study guide for the entire semester, except for Supernova week and Black Holes week next week. All right, any other questions? Okay, let's keep going. Last time we talked about the HR diagram in detail. We talked about it before exam 3. And actually, we're going to be talking about it all week. This is one from chapter 19.2, figure 5. We talked about this and a bunch of other ones. What I want to talk about now is something called the zero-age main sequence. And the zero-age main sequence is a theoretical construct based on what we scientists know about nuclear fusion. So what we do is, and here's a zero, this is kind of a color, it's kind of colored and, little stars in there and, stuff. This is a zero-age main sequence. What we do is we go to the guys at Los Alamos National Lab and the other big labs, and we ask them to figure out the theoretical properties of so many kilograms of hydrogen under the action of gravitation. In other words, a star. And so they work really hard on it, and they figure out what if you have a star the size of the sun, 1 solar mass, it'll have this much fusion. The size of the fusion core will be, so many kilometers. And then they do, all right, let's do 50 times the mass of the sun. And they make that, that's the one factor in their computer models. They're fairly simple. And I shouldn't say they're fairly simple, but that part of it is fairly simple. They just change the mass and then they recalculate everything. And so 50 times the mass of the sun. And then they do 100 times, so they figure out, all right, how big is the core? What's the temperature? And how long is it going to live? And so what they figure out is the approximate lifetime. And that's what this, every star on this has just started. This is kind of theoretical. It's an idealization. And they're saying that every little colored ball on this chart, from the reds all the way up to the big blue ones, is just started fusing yesterday, right? And what it says is the stuff up here towards the top left, these are the, let me get my cursor over here. Come on, baby. All right. These ones up here, these are the really heavy ones. Remember, these are the high mass stars. Down here are the reds. These are the low mass stars. They figured out, if you're up here in the upper part of the HR diagram, go ahead and make a diagonal line. And mark down, that's 10 million years up there at about, let's see, what was that? Maybe 30 times the mass of the sun. So that's about 10 million years lifetime. And then down here, our star, the sun is down here, 10 billion years for stuff around ours. Ours is a little bit above that. And then stuff down here, they run their computer program again. And what was this one? Let's try that. Down here at the bottom, it's 0.3 times the mass of the sun. So right here, it's about 0.3, maybe 0.5 or so. So something of that size, theoretically, it's going to keep, it's got a very small core. So they run their simulation. They figure, all right, we've got a core of so many kilometers, so much mass in that core, such and such a temperature, therefore such and such a fusion rate, therefore such and such a change in the mass, such and such a rate of accumulation of helium, et cetera, and it adds up to 100 billion years. So these little red stars down towards the bottom of the main sequence, they are going to be around for a long, long time. Matter of fact, the zero-age main sequence is kind of an idealized construct, but it's nice because it does give us leverage to figure out the age of various star clusters that we can see in the universe. Various globular clusters. Like I know you guys looked at the Beehive cluster a couple weeks ago. What did you guys look at last week? Beehive cluster? So anyways, so here's another look at it. This is figure 4 from chapter 22.1. So this one's not all dolled up with colors and stuff. The red line is the zero-age main sequence. So that's the theoretical construct. And we can also simulate the evolutionary tracks. So if you go up here to the top, go ahead and make a sketch of this and make a sketch of one evolutionary track up here. This is for 15 solar mass stars. And then do one like down here for 1 solar mass stars. Okay, so do this little curvy track. That's an evolutionary track. Do the surface temperature on the bottom and do the luminosity. Now this one's powers of 10, so This is 10 to the minus 2, 0.01, right down here at the bottom of the luminosity scale. So that's 1% of the luminosity of the sun. So this stuff down here is a few percent. Here's 1, that's 100%, so that's where the sun is. Okay. And then up here, 10 to the 4, that's 10,000 times the luminosity of the sun. And that corresponds to, you know, maybe a dozen or so, 15 solar masses. So draw on your zero-age main sequence, you know, from this side down up to the upper left, and then get this kind of upper squiggle for 15 solar masses. And get this one for 1. And you could do the other ones if you want, you know. Anyways, so these evolutionary tracks show where on the zero-age main sequence the theoretically a 1 solar mass star is going to start. And then as soon as it starts evolving off that track, we know how long that's going to take. It's going to take about 10 billion years here at about 1 solar mass. And after about 10 billion years, it's going to go up this way and go on up this way. And eventually ease on out here. Now up here, this is the red giant area. And this one up here, the reason I want you to do this one up here is because these are red supergiants up here. So this is like Betelgeuse territory up here. But regular red giant stars that are a little bit smaller, they kind of boost up into this zone here. Now, so kind of sketch that out. And that's and what we do is we look at a cluster, you know, like we're going to look at cluster M41 here in a second. And we plot up the HR diagram for as many stars as we can figure out in that cluster. Now, the advantage is that the cluster, if it's far away from us, the brightness, the relative brightness of each star in the cluster tells you the absolute brightness because they're all about the same distance. All right. So, and so if you can see, now, you know, when we look at all the stars in the Gaia HR diagram that we were looking at before, those are all different distances, and there's some close ones and there's some far ones. But if you can see a cluster, you know, like a globular cluster of some kind, all the stars there are going to be at the same distance. So the HR diagram is going to be really helpful. Now go ahead and make a sketch of this one. This is HR diagram, and the red line is the zero-H main sequence. So if all the stars are just starting out with fusion, they're going to be somewhere on or near that red line. All right? Now this is figure 5 from chapter 22.3. This is the globular cluster called M41. And so the luminosity, we could figure out the luminosity just because we know the approximate distance and the apparent brightness. So we can work out the luminosity. And notice that this one has a scale that goes up to 100,000 at the top. The one we were just looking at, this one, well, it kind of went up towards 100,000. This one goes up to 10 to the 5 and down to about 0.1. And so when you map out, now go ahead and make a diagonal line for the 0H main sequence, and then put a bunch of dots here. But then here's this one kind of snaking up here to the, starting right about here. All right, that's the main sequence turnoff point. These stars in the cluster, they're nice, but they don't actually fall on the 0H main sequence. They're kind of easing off towards the, and then here, up here, put a sprinkle of red giants up here. All right, so in that cluster, M41, there are some red giants already from the short-lived stars. And some of them are just kind of easing off. These are the ones medium lifetime. And these ones down here below the turnoff point, so here's the main sequence turnoff point. Here's the red giants. below the main sequence turnoff point, okay, whatever that happens to be, they're still on the main sequence. So they haven't reached their maximum lifetime. All right, so you look at that turnoff point and you think, all right, if the turnoff point is about 10 billion years, I should see G2 stars like the sun on this main sequence. But anything hotter than the sun, so OBAF, if I see those have migrated off a little bit or quite a bit, that part of the main sequence is empty. See this? Here's the main sequence turnoff. The main sequence up here is empty. And those are the fast-living stars. The bigger the star, the shorter its lifetime. So those have already turned into supergiants, maybe even gone into supernova. All right? They're kind of off this chart. But we still have these red giants up here. These guys, so these guys here, probably started, I don't know, right up at around in here maybe. All right? So astronomers use that position, the main sequence. That's your leverage. If you can see the main sequence and then compare it, of your cluster and look for the turnoff point, you can figure out the age of the cluster, roughly. And I know that when I was still in grad school, there was a big kerfuffle about this because when I was in grad school, the best known age for the universe, I think, was about 10 billion years for the age of the universe. But through looking at globular clusters, easy to observe, relatively easy to observe around our galaxy, we knew that there were clusters that were like 13 billion years old. Using the main sequence turnoff procedure. And so we were faced, in those days, we were faced with a real conundrum. Globular clusters that we could see and, see the main sequence turnoff and all that stuff that were actually older than the universe. So we knew that didn't make sense. So we continued observing and stuff, and what we did was observe the Big Bang. I shouldn't say we, other scientists observed the what we call the cosmic microwave background of the Big Bang. And I'll never forget, I was at this big black holes conference, and Stephen Hawking was there. And my dad flew out just to see that conference with Stephen. And all kinds of guys were there at this conference, big shots. I mean, relativity big shots. And I'm a grad student, so I'm not even a small shot. My boss, my research advisor he was a medium shot. Everybody knew who he was, but anyways, so we're at this meeting, and all of a sudden they published the results of this spacecraft that had measured the cosmic microwave background. And it went through the conference like wildfire. Did you hear that? And because they figured out, the exact temperature of the background radiation. And from that, they were able to figure out that the universe was about 13 or 14 billion years old. And therefore, the globular clusters were not older than the universe, and a lot more to boot. So there's a lot to be understood about all that stuff. But this is the thing that was sticking in everybody's craw. We knew that this was kosher, everything looked good, and we had these estimates of the age of the universe, and eventually our newer estimate, like we saw at that conference, came into agreement with the globular cluster ages. So here's kind of your strategy. This is figure 8. So when you see, so the figure on the right over here, that's the 0H main sequence. So theoretically, everything on in this globular cluster, or this grouping of stars, they just started fusing yesterday. All right. Now, if your main sequence, if your HR diagram looks like this, your main sequence turnoff is way up here, then that's at about the 100 million year lifetime mark. So that means that these stars, now remember, these stars up in the upper left of the HR diagram, they might not live more than 100 million years. So if that part of the main sequence is empty, then you could say, all right, this cluster of stars can't be much more than 100 million. Right? So you try to make an estimate. Right? But if you look at another sequence or another cluster of stars, and you see it, whoa, I've got a really deep turnoff point. Okay, so this cluster is about 10 billion years. Down here, I've got, because all the, most of the upper half, upper 2/3 of the main sequence is missing. All that stuff's evolved off into red giant, red supergiant, blah de blah, white dwarf, detonations. It's missing. Now the stuff that's older than, the stuff that's younger than 10 billion years is off. All right, the stuff that's, so the stuff that's going to stay on the main sequence for another few billion years, or even 100 billion years, is still on there. Right? Those are the little red stars. Right? So if we see a globular cluster with a bunch of good main sequence K and M's, that means it's a really old cluster. All right? And if we see a cluster with a lot of K and M's and then a bunch of red giants up here, that's a really old cluster. All right? So you can read about this in chapter 22. And I really love this diagram because it shows you the exact logic that astronomers use. All right, now here, let's apply it to this one. Here's M55. Now, if you look at this one, it's really, really loaded. So this is a globular cluster, M55, and it's in our galactic halo. So it's, our galaxy's like this swirling and burling spiral. But around the center of it is like this spherical halo that contains a lot of these globular clusters. M55 is one of the ones that we've studied a lot. It's a gravitationally bound object. So it basically orbits as a big blob. Kind of like our solar system is gravitationally bound. Right? So the Earth-Moon system is gravitationally bound. So we orbit together, kind of as a combo in orbit. Okay, and the same thing with this thing. All these things are gravitationally bound. So they orbit as a blob. And because it's at a blob, we can estimate the distance fairly well for all of them. We don't have to, try to triangulate on them all. If we get one or two distances, then we can, kind of ballpark it. And it's got about 100,000 stars, so that's a lot of stars to get an HR diagram. Because if you can get a distance, at least a distance estimate, you can figure out the luminosity. And you can always figure out the surface temperature just by looking at the color. So this one, as I said, the logic is look for what's missing from the main sequence when you plot up just these stars in this globular cluster. So don't use anything out in one of the spiral arms of the Milky Way. Don't use the sun. Just stick to the stars in the cluster, in this one. And there's 100,000 of them. And look for the stuff that's missing. All right, now here's what it looks like. This elbow in the data here, right? So this is M55. There's the main sequence turnoff right there. All right? That's our main sequence turnoff. And then these guys up here, these are blue giants, red, and all these things are evolving off the main sequence, but everything here is still on the main sequence. All right? Now, caveat, in this diagram, the vertical scale is absolute visual magnitude, and the color temperature horizontal scale is the B minus V color index. So don't worry about that. Just remember, luminosity scale on the vertical. Actually, they have it over here on the right. There's your solar luminosity. So this is 100 solar luminosities, 10, 1. So the sun is still down here. So M55 has still got stuff that's above the sun. So the sun is right about here, about 10 billion. So this thing's definitely not 10 billion years old. And you can figure out the age of it and stuff like that. Okay. So so that does not make no. I guess I'm not reading this right. I'm reading this a little bit. I can't see the perspective. Anyways, so 12.5 billion years is the cutoff term, and so this it looks a little bit, from my perspective here, it looks a little bit lower than it is. Right, so 12.5 billion years is the approximate age of M55. All right, so it's somewhere, somewhere up in, it's hard to get the, so this is 10 billion years, so the turnoff is right about here for M55, somewhere between 10 billion and 100 billion. Yeah, sun's right about here. All right. And we could do that for, we astronomers want to do that for as many places, as many globular clusters as we can do. All right. So here's another blurb about the logic. This means that there are no stars left near the top of the main sequence. Only the low mass stars near the bottom remain. The older the cluster, the lower the point on the main sequence, the lower the mass of the stars, where the stars begin to move toward the red giant region. All right. So McKeegan's particle is for stars that, no matter which, we don't know, how old it was, but it was somewhere over on the red giant branch, somewhere, where it started, we don't know, but. So that's from chapter 22.3, checking out the theory. That's a really nice chapter too. So, and it leads us into this idea. What happens during retirement, during his time off the main sequence? Well, a red giant star, if you have a smaller star that leaves the main sequence, and it's becoming giant star status, it starts fusing helium and other elements. The core gets a lot hotter. It expands the outer layers, and the outer layers are actually, it's hotter in the core, cooler on the surface, redder. Okay, so that's why they become red giants. And eventually, they become unstable. The outer layers become unstable. And the star will basically kind of blow the outer layers of the star. And these are called planetary nebula. This is a picture of a planetary nebula. All right? Now, they're not planets. The person that coined the term thought they were planets, but then somebody with a better telescope said, no, it's really something having to do with that star at the center. You can see it in the center of this thing. It's blowing its outer layers. Our star, most stars have something that we call solar wind. And the solar wind is what causes aurora borealis here on Earth. All the protons and electrons, helium nuclei and stuff, maybe a few regular atoms that go streaming off the surface of the sun because, they escape the magnetic field of the sun, the gravitational field of the sun, and they blaze past the Earth. It's like solar wind. It causes the aurora borealis. But if it's really strong, it can, Jenny, can you do this? If it's really strong, the solar wind can actually decrease the mass of the stars significantly. Now, our solar wind's not blowing that much. But the solar wind is moving out in a spherical manner, and it has gusts. We have satellites up that monitor the space weather, and they can measure the speed, believe it or not, of the gusts of solar wind. And this star's got really big gusts of solar wind. So the leftovers, after you blow those outer layers, your core stopped fusing eventually, and you're left with a really hot core, but it's not fusing. And that's what we call the white dwarf, and that's the thing at the very center of this image. And it's very hot in the ultraviolet. It's HOT. So we call it a white dwarf, but actually a lot of them are the peak in the ultraviolet. Okay? And it's not big enough, not dense enough to keep fusing, carbon or anything like that. So it's just kind of sitting there. But it's still really hot, and that the incandescent radiation, the thermal radiation from the surface of it, we can see it. It's just a small star, so it's not very bright. We call it a white dwarf. Here's a close-up of it. And here's the white dwarf at the center of this one. So it's still blowing a few layers. And these circles, like this one here, it looks like a circle in this view. That's actually a shock wave, we think. All right, so write down that word, shock waves. Shock waves are becoming very important at this stage in a star's life. Now, here's another one. This is called the Bubbly Nebula. This is blowing a bunch of layers. And just go to the astronomy picture of the day and use the search function, and just look up planetary nebula, and you'll see bunches of beautiful images. Here's another one, Ring Nebula. I think do you guys look at the Ring Nebula I think they look at Ring Nebula sometimes. Maybe fall semester they look at that. I don't know where that is off the top of my head. Here in the center you can see the white dwarf in there. Here's another one, Helix Nebula. So they don't look like all rings all the time. Sometimes they have asymmetries. Here's the same one. And this one is this image of Helix, I believe, is a composite with visible and X-ray. This one I think is visible. And you can see the white dwarf down there in the Helix Nebula. So these are smaller stars. And our star, the sun, will eventually blow its outer layers like this, billions of years from now. So we don't have anything to worry about before final exam week, but eventually it's going to blow layers. Now, after blowing off layers, what can happen for a low-mass star? Well, there could be some explosive supernova detonations. And I want to do a clicker question for you about nuclear fusion. Now, hopefully you'll remember, use your brain, or maybe go back in your notebook and to the time that we talked about nuclear fusion, E equals mc squared and all that stuff. Here's your question. Why is it that you get energy production from a fusion reaction? Read carefully. Didn't this used to be further over here? This TV. 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, 69% of you got it right. The answer is B. Let's take a look at the reason. Here's the 4 protons. Go ahead and make a sketch of this. 4 protons coming in. And then here's the output over here, a helium nucleus. Now that's 4 nucleons, so that's helium-4. And it has 2 protons, so it's a 4 upstairs, a 2 downstairs, and then He. Now the incoming protons are just a little bit heavier than the output helium-4 nucleus. And where does that missing matter go? It goes into energy. E equals mc squared. The missing matter, or the missing mass, becomes the energy that fuels fusion in the sun or anywhere else. So here's what happens with a white dwarf star. Fusion like that can cause something called a type 1a supernova detonation. And it's a catastrophic detonation. And type 1a, I'll just give you a couple specs on type 1a that you can write down. Type 1a supernova detonations, they're all about the same brightness no matter where you find them, because white dwarf stars have a very limited range in mass. So if you see a white dwarf anywhere in the universe, it's going to be somewhere between like about maybe 90% and 140% of the mass of the sun, right? Now that's the thing that goes into a nuclear detonation. And here's the second comment. The mass is all the same, so the brightness is all the same. Second comment, it's completely blown apart. It completely fuses. It's a catastrophic detonation. There's nothing left. You know, there's no smithereens, except for maybe the outer layers of whatever else is nearby. The white dwarf is gone. It's completely fused into energy. Comment number 3. Because of the first 2 concepts, supernova type 1a can be seen on the far side of the visible universe. If we're looking. If we're looking in the right spot, we can see them. They're very, very good. And because they're all about the same brightness, their apparent brightness here on Earth tells us the distance. So we can use them as a way of finding out enormous distances that we could never triangulate, no matter what we ever tried to do. We could never triangulate. But with these things, type 1a supernovas, we can get at least kind of a ballpark estimate of the distance of any galaxy that we can see with a type 1a supernova. Here's a nice diagram from the Chandra spacecraft website. Chandra is an X-ray observatory up in orbit. This is the problem. Oh boy, this is out of order. The white dwarf, if the surface of the white dwarf acquires enough hydrogen from its companion, here's the white dwarf right here, and here's the companion, all right? It can cause a thermonuclear detonation on the surface of the white dwarf, all right? So that's why I was asking, about the, hydrogen and helium fusion. Yeah, you can get, a white dwarf is what's left after the star has finished all its fusion. It's normal lifetime of fusion. It's blown its outer layers, and the core has stopped fusing, but it's still sitting there and it's really hot, but it'll eventually cool off. But if it has a companion star, or maybe a nebula that's pretty thick nearby, and it gets sucked into the surface of that white dwarf, you can create conditions that will cause a thermonuclear detonation. And once that starts, the whole star goes. The whole white dwarf is kablooey. All right, so now this thing over here, this is called the accretion disk. All right, now that's a word that you never see the word accretion, I never see it, anywhere outside the context of white dwarfs and black holes and stuff, neutron stars. But accretion disk basically means that if you have some companion, whether the companion's a giant or a regular main sequence star, if the white dwarf is close enough, it'll suck stuff in. But because most of these things are spinning, it'll acquire a disk-type shape. So there'll be some angular momentum. But then, when the conditions are right, you get a nuclear detonation. Now, the important thing about this is in this caption, right? The nuclear detonation occurs, the entire star is gone, all right? And those conditions of pressure and temperature and density, along with the original composition of the star, are right for very exotic nuclear reactions, right? The kind of nuclear reactions that build up gold. You know, the proton reaction that we were just asking about on the clicker question, 4 protons in, 1 helium nucleus out, that's a way of creating helium nuclei. And most stars in the universe, even the biggest ones, will not cook up any nuclei. Everything's cooking up helium. All stars are cooking up some helium. But, some stars will cook up carbon and nitrogen and oxygen and silicon and all the way up to iron. But they can't go faster. They can't go past iron on the periodic table unless you get into a supernova detonation like this. And then the conditions are, you can't get those conditions inside a star. But in a supernova detonation, the shock waves, yeah. All right, so make a note, shock waves. Okay, and then eventually that detonation will leave a visible remnant, and here's a kind of an artist's conception of a visible remnant. So these are the outgoing shock waves now that you see. And again, all kinds of exotic nuclear reactions all the way up the periodic table. Now, no supernova is the same, but we think that this is how many of the current abundances of heavy elements above iron are created in supernova detonations. Now, so that's the supernova remnant. And this is actually, sometimes we don't see the supernova, we just see the remnant. We can look across the sky and see supernova remnants all over the place. Here's one that we can see. This is an X-ray false color from the Chandra Observatory. This is actually a supernova that Kepler saw back, 400 years ago or so. So Kepler and Tycho Brahe saw one as well. All right. But this is the supernova remnant of Kepler's, and we think it's a type 1a. So in the middle of this thing used to be a white dwarf and some kind of companion, and they're gone now. All the smithereens. In this formation, it doesn't look like much. This doesn't look like much to see in the visible wavelengths. This is false color X-ray. It's very luminous in X-ray. And I'll just challenge you if you want. Just go to the Chandra website. It's loaded with really cool images, and visible and X-ray, and I think they have some ultraviolet images in there too. They put together composite images. Here's another one, type 1A, RCW 86. Now this one was not seen by Kepler, it was seen by Chinese observers back in 185. You know, we have a record of it. They mentioned it, a guest star, and in 185 AD. And I don't know if they made any pictures of it, but you can see sometimes, you know, mentions of it in ancient historical writings. Anyways, 185 AD. And this is the remnant of what they saw. And they think that this one, you know, by now observing the elements, the quantum fingerprints in this supernova remnant, and this one's composite. This is X-ray, visible, and I think it's infrared as well. You can look it up. Look up RCW 86. And, you know, the other good place to look is Astronomy Picture of the Day. Very good. So there's all kinds of elements, and we think that the mixture of elements in this one also indicates that this one was a type 1A. So somewhere down in here, boy, this looks like garbage. This one looks good. It looks so much better. Just type in RCW 86 and Chandra and look at the pictures on your own computer. I mean, my computer screen, it looks great, but this is weak on the computer, on this display for the lecture hall. Anyways, go ahead and look at that. We think is type 1A, somewhere in here in the middle was a white dwarf and a companion of some kind. All right, now I mentioned the elements manufactured in type 1A and other supernova detonations. Let's take a look at the periodic table. All right. So go ahead and make some notes, periodic table of the elements. Most abundant in the universe, hydrogen and helium, first two. All right. And in the crust of the earth, all right, so this is like the crust of the earth and like all the molten lava from Mount Vesuvius and stuff. The most abundant are oxygen, silicon, and aluminum. So oxygen, go ahead and write this down. In the crust of the earth, oxygen is 46% by weight. Isn't that amazing? You know, we think about oxygen as something that we need to breathe, which we do. But yet it's also this huge component of the crust of the earth. Silicon, 28% by weight. All right? Silicon dioxide, sand. No wonder we see it all over the place. Sand. Silicate. Any kind of a mineral has got silicons and oxygens out the wazoo. All right. Aluminum, 8% by weight. All right. Now, so when we take an assay of the universe at large, we see mostly hydrogen and helium, and a small fraction of a percent is all the other elements. And that's when we look at the universe in its entirety, in the visible universe anyways. The crust of the earth, you know, we look at rocks and analyze rocks, you know, the stuff that comes up from oil wells and gas wells and stuff, mines, as deep as we can go into the crust, and it's oxygen, silicon, and aluminum. Massive star cores, massive stars. So the sun doesn't do much of this, but something, you know, up in the area 15 times the mass of the sun, yeah, you're going to get plenty of other elements up to iron 56. Now let's take a look at that. All right, here's all, just go ahead and rope in all the elements up to iron Fe, iron 56. Now, this is stars on the main sequence. Now, they're not going to make a lot of iron 56, But stuff above that, and here's the interesting thing. All those type 1A supernova remnants, you know what they can see a lot of in X-ray? This is kind of interesting. The 2 spaces over from iron, they can see radioactive nickel that's been made in a supernova detonation and is now decaying radioactively into cobalt and then back into iron. And the X-rays that it emits as it decays are what they pick up in these supernova remnants in the X-ray. So, and you know, that's not the only thing they pick up, but that's one of the signatures that they look at. It's kind of cool. And you might be thinking to yourself, well, Dr. B, what's significant about it being 2 spaces over? Go ahead and write that in your notes. Why is nickel 2 spaces over from iron important? Why are those 2 spaces important? Because if you fuse an iron nucleus with a helium nucleus, it's going to bump it 2 spaces. It's not going to, you know, if you fuse an iron nucleus with a proton, that'll produce a cobalt 1 space over. But we got buku helium nuclei. If you fuse those babies together, a good old iron 26 and 1 helium nucleus, bing, you got a nickel 28 nucleus. And then, but that'll form, and then it'll tend to decay radioactively. It won't necessarily be stable. All right. At least the form that is formed in the shock waves. Let me repeat that word, shock waves. All of this stuff. And do you simulate shock waves? Ooh, that's probably not a good model then. Oh, okay. Somebody's doing it, I bet. The shock waves in these, when I say the word shock wave, you know what you've probably heard shock waves a time or two. Sonic boom. You know, like raise your hand if you've ever heard the sonic boom, double sonic boom from the space shuttle when it comes to land. Okay, it's kind of cool. Those sonic booms are shock waves. The air pressure goes way up and then way down again over the space of a few centimeters. And in the case of a supernova detonation, probably a few kilometers. The shock wave dynamics are extremely difficult to model on a computer. Very challenging. Even more difficult than the stuff that I did in relativity and quantum field theory. But we're trying to figure all that stuff out. Shock waves, shock waves, shock waves. All over the place. Planetary nebula, nah, those aren't really shock waves. Maybe weak shock waves, I guess. But supernovas, shock wave city, baby. You gotta. And when you get a shock wave, you're going to get a lot of radioactive nickel, my friend. Now, when we come back on Thursday, the trouble with iron. We got more trouble to come in supernova week. That'll be the core collapse and neutron star supernova process. You're dismissed. I'll see you on Thursday. The trouble with iron.